So this topic is on Petri nets. So we have looked at different techniques for mathematical modeling of systems, right. We have seen the basic queuing networks or queuing systems with MM1 queues and Markov chains. We have looked at closed queuing networks and MVA and the related techniques. So Petri nets is another form of mathematical modeling to formally specify a particular system, right. Not only specification, we can also derive some performance results also from this Petri net modeling. So it is very similar to Markov chains in that sense in terms of applications, right. We can essentially model the behavior of a system and then try to derive some properties from that particular model. So the name Petri nets arises because this was invented by I guess Carl Adam Petri, I guess we can say invented because he came up with this. And if you look at Wikipedia for this page on Petri, he has written that one page on himself, and he says he actually discovered, he came up with this in when he was about 13 years old, the 1930s, but then he formally made it as a presentation in 1962 as part of his PhD thesis. Okay, so we do not know about how true it is, whether he came up with this in his 13th year or not. We will simply use, right, 1962 as the age when as the time when this was actually formally announced to the world, right. This is as part of his PhD thesis. The PhD thesis itself was published in 1966, but the ideas were originally conceived in 1962. Okay, so this, as we said, right, used to model the behavior of a system, right, model the functionality / behavior of a system, and what that system is, we will see examples of those systems as we go along. Okay, and if you in terms of applications, right, there are a lot of domains where this can be applied. One, of course, we know our computer systems where we can actually model this, computer communication networks we can model, right. So we can look at computer systems, the types that we saw before that we modeled with MVA and so on, are computer communication networks, right. So computer networks, protocols, and related fields, but in addition it has got a lot of other applications in like manufacturing, for example, right. If you look at some of the examples, you will very clearly see that, just like any computer processing system can also be mapped to a manufacturing system where there are parts, there are components, and you have to do some processing on those components and then, right, combine those parts into a different system. So manufacturing systems, production systems, where you actually manufacture parts and then turn them into products at some end, and also sophisticated scheduling systems, right. This is scheduling not from merely our computer systems networks form of scheduling, but also scheduling in terms of jobs in shops, right, where the machines available and jobs to be processed on the machines, and we need some sort of scheduling systems there. Also controllers, right. So we can look at controllers as in your PLC controllers that we see, right, embedded controllers that we see on various devices, the programmable logic controllers, right. So those can also be modeled, the behavior of those can be modeled with the help of Petri nets. That is the basic or some of the applications that you can see with that can be dealt with using Petri nets. Okay, so that is the first part of who came up with it and what it can be potentially used for. Okay, so now let us look at what is the formal definition, right. So a Petri net, we are going to use Pn to represent the Petri net, right. So Petri net is a formal language, okay. So it is a formal language to represent a system. It is also a graphical language. So by looking at the system graph, just like state machines, right, state machine is also a graphical means of representing system behavior. This is also a graphical language, and this is especially for modeling systems with concurrency. This is what is key, right. How do you deal with concurrent systems modeling? And if you go back to the 1960s, computer science and concurrency at that time were probably just people are just talking about it, right. We do not use concurrency as we use today, where multi-threaded systems are very common, or parallel systems have become quite common. And so this is systems where there are concurrent operations going on, concurrent processes that are going on that communicate with each other, and you want to understand if because of this concurrent processing, right. For example, we will see examples in terms of right, the basic threading and things like that. So, but that is the basic idea, right. Wherever there is concurrency, you can try to use this PetriNet system to model the system behavior, and from that derive some sort of performance metrics. Okay. So formally, so PetriNet, if you were to talk about in a graphical or in a graph theory terms, is a bipartite graph. So it is a bipartite graph, okay, containing two types of nodes, and then you have graphs connecting those two types of nodes. Okay. So the two types of nodes are, so the node types or vertex types called places. Okay. So place is one type, place is whatever, it is a place where you store something, store a token, for example, think of it as a box or a buffer, something that holds something. Okay. So that is called a place, and this can also be used to think in terms of system state, right. So this represents some sort of condition that has to be satisfied, right, in the communication, in the process that we are trying to model. So place is the term that we are going to use, and the next term is transition. Okay. So transition is the other node type in this bipartite graph, and a transition essentially represents some event that occurs or some processing activity that takes place. Okay. So there are items held in places, and on those items, when some conditions are satisfied, a transition will trigger, a transition will occur, and that transition, as the name implies, will change the state from change the system from one state to some other state. Okay. So that is transition, and the transition, like I said, corresponds to some sort of activity. So for example, if you look at, say, the user program is waiting for data, right, waiting for some input from the keyboard. So as soon as the keyboard input arrives, it gets stored in a keyboard buffer, right, or in the system kernel buffer corresponding to the keyboard, and then you have some logic that works on that character that are characters read from the keyboard. So that processing is the activity, that is the transition that takes your input keyboard values and then converts that to some other value, right. So for example, user types in X as input, the processing is, say, output X squared. So the logic is represented by the transition, and then it then in turn produces output is X squared, so that goes to some other place. So that is, these are the two main components, place and transition. Okay. And we use circle to denote places, and the transitions, there are different ways. We normally simply draw a straight line to represent a transition, or sometimes little rectangle, right, thin rectangle like that to represent a transition, and there are differences where or sometimes just people use even boxes to represent transitions. We are going to use this straight line to represent transitions. The places are simply circles. Okay. And inside this place, inside this box, you can find tokens, right, that is the other component of the system. So there are places and transitions, and there are tokens that circulate between these places in the system via these transitions. Okay, transitions are like gates, and it goes from place to place through these different gates, and the gate can be opened only when certain conditions are met. That is the basic idea, otherwise the gate is kept closed, right. So when the gate opens, the horse jumps from one part of the field to the other part of the field, right. So that is the basic idea. Okay. So now these are the two node types in our bipartite graph. So what else do we need in a bipartite graph? The edges, right, the arcs that connect these two node types. Okay. So we have now, so the places and transitions are connected by directed edges, or we also call them arcs. Right. So this is a directed bipartite graph. Okay. So now let us okay. So the arc can exist only between a place and a transition and vice versa, but you cannot have an arc between two places, that is why it is a bipartite graph, right, otherwise it is so the arc exists only between a place and a transition or vice versa. Okay. So that these are that is it, this basically defines this notion of, and then we have of course tokens, right. So tokens circulate in the system between places. So these are the basic entities that are available in the system. So next let us look at a simple example, right, that or a figure as to show what is going on. Okay. So here is a place, here is another place, there is this place is one token, this place has two tokens, okay. Here is a transition, and we are stating that there is an arc connecting this place to this transition and this place to this transition, okay. And then from this transition you can have output transitions that go to other places, okay. So this is your basic model of the system components. So these are on the left are input places with respect to this particular transition, right. This input place could be an output place for some other transition. For this given transition, this is the input place, and then these are your output places. Okay, and this is the token in the system. So tokens get created in these places and they get moved around in the system as we go along. Now when does a transition take place, right? So the simplest rule for a transition to take place is that as long as there is, if there are say multiple input places for a given transition, if there is one token present in, at least one token present in all the input places that are connected to a transition, then the transition will fire. And as a result of the transition, what will happen is one token will be removed from here, one token will be removed from here, and then you will be placing one token here and one token there, and the number of inputs, number of outputs need not be equal. I can have less number of input places and more number of output places, vice versa. All we are saying is when a transition occurs, I delete tokens from all the input places and add one token to all the output places. That is a very basic definition of what happens. We can make this more complex later on by doing multiple tokens and things like that, but simply speaking that is when a transition occurs. Whenever there is an input in this, basically all these conditions have to be true, that is what it says, right. When all these conditions are true, the transition fires. As a result of the transition, some values get deposited in these corresponding output places, okay. So implicitly there is copying and things like that going on, but as far as system goes, a token is going to be created in each of those output places. Is that clear? Questions? No. Okay. So we will write it down now. So transition triggers in the basic definition, we say triggered or fired, right, whenever there is at least one token in all the input places, in all its input places, that is one, okay. And once fired, one token is removed from all the input places and one token is added in or added to all output places. I would say all its input places is added to all of its output places. That is the fundamental thing of a transition. Now there are lots of hidden details, right. when does a or how long does a transition take to fire? Is it instantaneous, right? When a transition fires, immediately does the packet get delivered, or is there a delay, right? Processing delay. If you look at a transition as an event or an activity, naturally it cannot be instantaneous, right? Sometimes it can be, sometimes it need not be. So all those other extensions will come later on, but that is the basic notion of what a transition is as far as system is concerned. Okay, so we will sort of go through some examples, right? So in other words, all the input, and as I said, the input arcs represent conditions, right, that have to be satisfied for this event or transition to be activated. That is what this basic definition is. Okay. So if you can interpret the input places as preconditions. If you remember, when we write this in C program, in programs in general, right, we talk about preconditions. So preconditions, when they are satisfied, right, only then this function can be executed, right. So they represent the preconditions, and the output places represent the post conditions. This is in terms of our programming terminology. Right, so post conditions could be, right, the number of items in the buffer is x plus 1, before it was x, after that it is x plus 1, those are the pre-post conditions. Okay. So for example, if I were to say, right, this is a simple system, right, so this is the input place, that is the output place. So this is before firing, let us say this is T1, right, this is P1 and this is P2. So before firing of T1, this is what the system state was. Then after firing, system state will find this empty and this will have one buffer. So P2 will have a token, P1 will have no token. In case P1 had more tokens, 2 tokens, in that case P1 will still have one more token left, but P2 will have this one extra token added, right. So that is the basic, right. So by default one token is removed and one token is added to the corresponding, to those input and output places. Okay. So that is the, so formally if I want to represent this, right, so this is a graph. So any questions on this basic representation so far, right. So activation happens, one token is removed from all the input, one token is added to all the output places. Okay. So again, to state this formally, right, a Petri net we call Pn is defined by a 4 tuple. There is P, there is T, there is I, there is O. Okay. These are the components of the Petri net. So what is P? P is the set of places, and that is represented by P1, P2 up to Pm, right. So M is the cardinality of places. So there are M places in the system. T is the set of transitions, and there are N transitions in the system. So we will call them T1 to Tn. Okay. So what is this I and O? Any idea what I could be? All the input places, right. So what would be the, what would I be? I am sorry, it will be the set of input places. Now for every transition, right, I could have one or more of the input places connected, right, and I have N such transitions. So there are M places and N transition. So what could be this I be? A matrix, right, a matrix of whatever M by N or N by M. Okay. So this I is a matrix that basically tells you which are the different places, input places that are associated with the corresponding transition. Okay. And the entries will be either 1 or 0, right. in the basic case. We can have more sophisticated cases later on based on multiplicity of the arcs and things like that, but basically this is just your connectivity matrix, right. This is your set of gauges in the system, because this is a directed graph, I need to provide one this way and one for the other. So these are all the inputs, right. So for example I might say that P1 and P2 are inputs to transition 1, and maybe P2 and P4 and maybe PM are inputs to transition 2 and so on, right. So some sort of structure is there. This is the input, this is your definition. You have to come up with this, given a problem, given a system, you model the system, and then part of this, as end of that modeling, you will come up with this particular matrix, okay. And likewise you have the O matrix also, which will specify for each transition what are the corresponding. So same thing, the rows are the same and the columns are the same. So it is possible that at the end of transition, right, you will have, and if you look at it, there is technically no loop yet, right, these are loopless. You do not want to go from an input place to the input and output places are, you can have loops, they are allowed, but for now let us assume that this is a loopless system, right, where the output places are different from the input places. So like this could be anything, right, so this could be just 1 0 0 0 and things like that, okay. So these are your specifications for the network itself, okay. So this is now a static definition of the system, of this network. With only this definition, what can you do? You cannot do anything, okay. We need to have something, we need something dynamic in the system, right. What is the dynamic part? Where does dynamism come in? When you bring in tokens. So now the system state is captured by the number of tokens that are present in all those different M places, right. So there are, right, M places, and like if you look at the CPU disk problem, there is one CPU queue and there are 4 disk queues, right. So the system state is captured by the number of jobs in each of those 4 queues, each of those queues, right, so the 5 queues in total, that is the system state, right. So therefore the static definition of a system is this, but you will have to also bring in the dynamic definition. So we will have to add one more tuple to this, okay. So that is what is called as a marking, okay. So we will define a marking, okay. So a marking of a Petri net at time t, we will associate, because this is technically moving through time, right. So at time t, the marking of a system is simply given by the number of tokens present in each of those various places. Okay. So where mi of t is the number of tokens in place I at time t. This is the definition of a marking of the system. So this represents the current active state of the system, right, dynamic state or the dynamic state of the system itself, right. And then we use this, so when we start, just like in the case of state transition the Markov chain, right, or state transition diagram, we always have to say what the initial state is, right. You have to start somewhere, there is a big chain, big graph there, different states are connected to different waves, we always say that this is the initial state, right. So in addition to the set of the state transition matrix, you also specify the starting state. So likewise you also have to provide the initial marking of the system, right. So at some time t0, which is the initial time, right, m of t0 represents the initial marking. There is a little bit of confusion here because this m is appearing both as the number of places as well as the marking of the system, right. So just bear with that. We know when we say marking that m, when I use the term m in terms for the number of places, we are talking about the other m, okay. So this is basically, so now your the Petri net definition will now actually include your set of places, set of transitions, input matrix, output matrix, as well as m of t0. So now if I give this to you saying this is where this is my starting state of the system. So normally you will start with maybe 1 token in one of those places or 9 tokens in the case of the CPU disk example, right. I have to put 9 tokens somewhere. If you remember MBA we did the same thing, right. How do you find out the number of jobs in each of those queues? We start by simply saying that all the jobs n are equally divided among all those m queues. So it is n by m is the starting state, then you iterate and find out the steady state in terms of number of distributions. Likewise we will start with say putting all the 9 jobs in the CPU queue and then see how the system progresses with time, and finally you will come to a steady state system. So that could be m of t0, right. So that is your initial marking of the system, okay. Okay. So from this initial marking then what will happen is we can fire transitions. There are various transitions that are possible because these are all transitions in parallel, right. So different combinations of transitions can take place, and then the state of the system, the marking of this Petri net keeps changing with time, and that is something that we will now try to study and evolve. That is the main thing, right. So given the Petri net, given the initial marking, what is the sequence of markings that this system will go through? Will the system lead to deadlock, right, or if it does not lead to deadlock, what is the probability of the system being in a given marked state at a given point in time? All those things is what we want to find out, and those will translate to our performance metrics. Okay. So let us look at a few more examples and some sort of classifications of the Petri net components. Okay. So questions? No? Okay. So let us look at one Petri net, right, which is basically a system which is assume that there is a machine, right, that can be loaded and that will do some processing, and then after that it will do some unloading. We can think of this as a machine, or as computer science terms this is just a CPU that is processing something, right. So here is data is available, it gets processed, then it gets dumped in some post processed buffer where it can be taken for printing or something like that, okay. So and then remember there is also a loop in this particular system, okay. So we have 3 states, 3 places, P1, P2, P3, and then there are 2 transitions. Oh sorry, I am missing a transition. Okay, let us go back, and we need 3 transitions, right, because I cannot go from transition to transition, right, wrong, okay. We will go back and draw this again. There is P1, T1, that is 1, we go to P2, that is the next storage place, and then that goes to the next transition which is P2, then it goes to P3, then it goes to yet another transition T3, which then finally loops back to, okay. So this is the static definition of the system, these are all the nodes and corresponding arcs that is defined. So now when I bring in, let us say the initial state is 1 0 0, okay. So the initial state m of t0 is equal to 1 0 0, okay. So what that is the initial state. Now the input matrix will, let's say the I matrix will be what will the I matrix look like? Remember the I matrix rows are all transitions, right. So T1, what are the input places? Only P1, right. So only P1, others are 0 0, T2 0 1 0 0 0 1, right. This is our standard graph representation, right, because when I have to input this to a system I should specify that, right. So you think about it in terms of programming, right. If I had to give you this model, this is the way I will give the inputs to you, this is a representation of the Petri net system, right. I will tell you the set of places and transitions, and likewise O is what is the output? 0 1 0 0 0 1 1 0 0, that is all, right. This now completely specifies my input the Petri net as such, okay. So P is the set of, so if you want to be more complete, P is the set of states P1 P2 P3, that is input, then T is T1 T2 T3, okay. This is also given to us. So now with the representation as well as the initial values, we have to look for some properties of this Petri net, because we ultimately our goal is to get some sort of performance results from this system, right. Okay, I think I did something I am not supposed to, alright. Is that clear? Questions? Okay. Now there are different types of I guess subcomponents of the system, right. So we will just talk about some of those things in sequence. Okay. So for example, you could have a sequential action. This is very straightforward, where there is a place that feeds a transition, which in fact feeds, like this is just a sequential action, right. Data comes in, it's processed here, gets processed here, and finally gets stored there. And it is possible that you can have a system with a transition with no input. Okay, that is something we have not yet talked about, but I can have a system like this. I can even have a system like that, where the first transition has no input at all, which means it will keep on triggering, right. So it is just like a while loop, it just keeps triggering. Only thing is, if I add some delay to this, if each transition takes some time, say 5 milliseconds or exponential time with some mean 10 milliseconds, then that is the processing time for that particular system, right. And then it gets and puts so whenever it generates something, it puts the token here, and then whenever there is a token, it will be simply picked up by this transition. As long as there is one token, this transition will fire, and after it processes it, there is nothing for it to output in the system. Okay, this is also a very simple sequential action. And do you know what this can represent? If I tell you that the time spent in each of those transitions, right, is exponential with the parameter lambda or parameter mu, what could this be? What could this be? What could the system be? Any ideas? MM1Q, right? Because this is exponential time. This is your packet arrival process, right? So every one exponential, right, every 1 hour lambda with mean 1 hour lambda, you generate a packet. When a packet comes, it goes here. Whenever this queue is not empty, this is a server. This is the arrival process, this is a server process, right. And whenever it picks up a packet for processing, customer for processing, it spends 1 hour mute or mean 1 hour mute time on that process, and then that is it, there is no output, you do not really care about it, right. This is your basic MM1Q if you look at it, okay, where there is no input and where there is no output. So this is actually representing an MM1Q system. Now the question is, what do we do with this, right? How do we use this for performance evaluation? We will come to that later on. Okay, we will look at, so the initial marking of the system would be simply 0, right? Initial marking is 0, no customers in the system. So we will have to define what the state of the system is and see how we go through these different markings of the system. So what are all the possible markings for the system? The marking for the system is the number of tokens, right, in this place. It could be 0, 1, 2, 3 up to infinity, right. That marking represents the state of the system, right. So those are all the number of items stored in this place is simply the number of customers in the queue, right, or number of customers waiting in queue, because this transition implies that it is always processing someone, right. This transition will be fired whenever it finishes a particular. So this will be not fired if this queue is empty. As long as queue is non-empty, it will simply pick up the next process. Okay, and now is that clear? Why this is an MM1 queue? And implicitly, I have not really defined one more thing. If there are, say, 3 tokens in this queue, right, which of those tokens is going to get selected for processing? That is again scheduling discipline. So implicitly, we are assuming it is FCFS, but we can also bring in other scheduling disciplines. Okay, so we are saying that by this definition, as long as there is one packet in this queue, I will start processing it, and then if there is more than one packet, then this representation does not tell us anything at all. It simply says one of them will be selected, but the idea is that it is a FCFS, or it could be some other queue too. That is something we will have to bring in when we do the analysis part of the system. So that is so called sequential action, where one action finishes, it goes to the, this is like a pipeline, right, simply keeps processing. These are all the processing steps in the pipeline. So as you can see, you can now use this representation for modeling a pipeline, for finding a throughput of a pipeline, finding out where the bottleneck in this pipeline is. All those things you can actually try to find out. Okay. So then we have dependency. So a dependent transition is what we had seen before, when there are more than one input places. Okay. So this is So when all these places have tokens, at least one token, then you will generate, then this transition will trigger and then you will go and process that. So this, let us say that this means that some data, let us say I have not done a parallel, I have done some parallel processing, okay, there is some processing here which I am not showing, and let us say that I am searching for something, right. So I have given the search item to some different databases and they all have to come back to me with their respective results in the corresponding databases, and then this would represent a join operation, right. If you look at process fork and join, this is like a join operation where as long as all these places have the corresponding data values, I can take them and start processing them, right, that is what this represents. So if you look at it as a multi-threaded operation, that is what this is. These are all different threads, they have completed and placed some data item here for further processing, and this will not proceed until all these are having at least one token, then it will proceed further, right. Now, so there is implicit semantics, right. Some of the semantics are not clearly stated from the diagram itself, but these are all the implicit semantics. The only difference is compared to say UML, or maybe it is not a fair comparison, at least in this case the semantics are well defined. Once the semantics are well defined, then you can implement systems that will understand, interpret and parse a given Petri net and then give you results, right. Only when the semantics are not clearly defined you have problems, right. When we for example draw our own diagrams, we will have different interpretation for the same diagram, but here the interpretations are fixed. This is the semantics for this particular syntax that we are drawing here, okay. So this is a dependency class or dependency form of transition. Questions? Okay. Now sometimes we end up with conflict situations, okay, which is also not uncommon in programming and systems that we build. So what would be a conflict? So here is a transition that is expecting input from two different places, and if that, right, this is one transition. Now if I have another transition which is also doing the same thing except that there is this extra line, okay, two transitions but one common place between those two transitions, okay. Now if there is only data here and here, okay, let us call this P1, P2 and P3, right. So if P1 and P2, this is say T1, T2, right. So if P1 and P2 have tokens but not P3, if P3 does not have a token, then what will happen? T1 is fired, right, because T1's conditions are met. Likewise if P2 and P3 have tokens but not P1, then what happens? T2 is fired. So that is clear, the system knows how to resolve this. What happens if all three have tokens at a given instant of time, all three have tokens, then what should happen? There is a conflict, right. So now both the events or transitions can be fired. So now there has to be an additional policy, some other specification that either says T1 is higher priority than T2 or some probability has to be defined saying T1 probability is 0.5 or 0.9, T2 probability is 0.1. So there is a probabilistic way of transition or triggering a transition when there are multiple simultaneous transitions in conflict, right. You can have multiple transitions at different places of the network when there is no conflict. When they are conflicting, then you have to have a conflict resolution policy, right. So that is again this you will find, right, you will find in cases when such a scenario occurs, then there has to be some other mechanism that specifies how to resolve this particular conflict, okay. Is that clear? Any questions on conflict? Then now we come to our sort of, right, concurrency, because we said that concurrency is one of the key things. So how do we model concurrency in a particular system, okay. So let us say that I have to do this parallel processing, I am given a value x, okay, and I have to compare whether n or two numbers n and x is the input to the system, okay, and I have to compare and say whether n to the power x is greater or x to the power n is greater, okay. I can do that sequentially, I can do that in parallel, right. So that is what this will try to represent. So here so now the data is the token will contain two values, a tuple, right. So as long as there is one token available for processing, this transition will trigger, and like we said before, if I have something like this, the token will be placed in both these places, right. If this transition triggers, a copy of this data will technically go to both the places. That is the semantics that we have agreed upon. So when all the output places will get one token each, and what the contents of the token is simply the token that is present, some token however that is defined, right. So that is something that we will have to define, and so here it is. So this is getting processed, this is also processing, right. This guy computes n of x, this is computing x of n, and then they place the results here in this corresponding places. Now here is again what we saw before, right. So this is like I said, so this is like a join operation. When both these values are ready, this transition will trigger, and then you finally put that in the output thing. So this is how what we call as concurrency, right. This is how you model concurrency in the system. So this is pretty much all your concurrency right operations can be modeled as follows. Okay, questions on that? Now when we talk about concurrency, what is also important? Some other activity should also come into play, right. What is that? When two systems, two processes are sharing something, we have to model sharing of variables, right. How do you share? How do we model resource sharing? Our classic producer consumer problem, right. So producer is producing data, okay. So normally what you will say, producer produces data, gets into a buffer, right, and then it gets I do not know, right, some processing is done to that, or it could be something else, two other processes that want to update the same variable, something of that nature, right. So how do we do that? So I have two such processes that are doing some kind of processing. Okay, we have got all the transitions right here. Okay, now there is a shared token, shared variable. Only thing is I need to enforce mutual exclusion. I cannot have the same variable used by these two at the same time. Okay, so to do that we can represent it this way. Does this graph make any sense? So this is where the right. So what happens is, right, for this transition to trigger, right, what are the conditions? It needs an input from this place and an input from this place, okay, and then the result of that computation is stored here, okay, and after it gets stored, then it gets then once there is an item here, right, then it will trigger, as long as there is one item here, it will trigger this transition. Now what will happen is a copy will go to further processing for this particular process, but the original data is essentially returned back to the shared buffer, right. This represents the shared space, okay. So as long as there is an item here only can this one be triggered, okay. If there is only one item here, so if this is the case, when this condition is satisfied, now what is happening is you actually have conflict here, right. You have a conflict here, because if this is the case, which of these two is going to get triggered? Any one of them. In Unix or whatever systems, we handle it with the help of mutex. They both ask for the lock at the same time, one of them gets it, one of them does not, right. So assume that when this was the case, that this is the one that gets selected, okay. This is selected and the data gets forwarded here, and then it gets processed here, and then the copy returns back to the buffer that we started. Then what will happen again? Now then this transition can then trigger after that, right. So this is step 1, gets processed here, and then it comes back here. Now that the data item is available, there is also data item available here, then this can get processed and then get stored, and then the next transition triggers, and then after that we simply return that data back here, right. That is one way of capturing resource sharing. Now the semantics is important, right. Implementing this in a tool, okay, you have to make sure that these are all clearly stated, and how is this conflict resolution going to be done is also very important. It could be simply random, any one of them, which is what will happen in a mutex case, right. Either one can get it unless there is a specific priority associated with those. So that is how you would handle, you can model resource sharing. So like this there are a lot of other variations also. So how do we handle buffers? Okay, how do we capture a limited size buffer mm1b? How would we model that? If you remember, counter, put some restriction on the number of tokens. So, it has to be some other additional semantics that comes in. So, let us try this particular thing. So, here token is produced and that token normally gets stored in this buffer, but let us say that this buffer there is some capacity, this is a maximum number of tokens available. So, here is some input buffer where we can sort of store endlessly. So, this is P1, this is T1, this is P2, but I want to make sure that in this P2 part of the system I should have exactly or at most B buffers. I cannot handle more than that. Okay, this is what happens. This is like a processing, right? Arrival comes in, this is processing, or the server is selecting the packet. Okay, and then once the processing happens, it goes on to some other part of the system, right? That is something that we do not care about. So, what we do is when P2 finishes, we introduce this another placeholder called P3 that will feed back to this T1, similar to the resource sharing example we saw before. Okay, now the condition is that P2 plus P3, right, should have less than or equal to B. Okay, this is the way I can emulate a buffer in the system. So, this again something, this is part of the specification, right. So, I have to not only draw this diagram, also put in some other data that explains that this is the meaning, right. So, I have to have some other notations to capture that. So, if I do that, then what happens initially, where will let us say B equals say 3, okay, let B equals 3. Initially what will be the system state initial marking, where will those 3 tokens be? P1, no, P1 is input, it is coming here. So, there is some input process, it is generating. This P2 is where I am worried about, this is where this is actual storage before it goes to the server, right. So, this could be infinite, I am not yet thinking about that, this is where I want to control, and I want to see at most 3 packets in P2, P3 combined. Okay. So, where will I put those 3 tokens? P3. So, I will put the 3 tokens here. Okay, I put the 3 tokens there, right. So, this is empty. Now, what will happen? Can this T1 fire? T1 cannot fire unless there is an input that is generated, right. So, let me try red. So, input arrives. Okay, this is input. Okay, what happens now? I will, there is at least one token here, at least one token here, and therefore this transition will now fire. So, when that transition fires, this token is removed, one token is removed, and where is the token now added? Token gets added there, right. So, P2 has one token. So, what will happen? It is going to get processed by this transition T2. So, after processing, right, when this transition T2 finally triggers and completes, what will happen? This packet is now processed and it is going on to next destination. At the same time, you are now returning, right, the token here, that is what you try to do. So, therefore, in the instant of time that only process this one packet, there there were 2 tokens sitting here, there is one here, so collectively we had 3, right. But we could also have the scenario where the opposite is also true, right. So, it is possible that I will have say no packets here, and let us say that currently I have 3 packets sitting there, that looks like a smiley. Okay. So, there are 3 packets sitting in P2, which means there is no packet sitting in P3. So, what happens if a new packet comes in? Can it trigger? New packet cannot get triggered. Why? Because there is nothing in P3. So, when will P3 get one token? Only when one process that is, or one token that is getting processed in T2 finishes and comes back to P3. That is how you can model a system with a buffer. Is that understood, right? So, that is a neat way of trying to, but only thing is we have to have a mechanism of specifying that this P3, P2, P3 are tied together, and there is this extra condition, right. So, this is now additional restraints on the system that you have to tell the underlying implement under the underlying tool to be able to process that correctly. Okay. Okay. So, questions on this part? No? Now can I simplify this to represent my MM1B? With what remember we saw MM1, right? I had just had 2 transitions and 1 place in between. Now can I do the same thing? How do I convert this to MM1B? Is there any way I can do that? I do not need an input place, I do not need anything to hold the input, right. So this is a transition T1 with parameter lambda exponential, right. This is implicitly exponential. Actually this is a special class of network, this is not a general Petri, this is a stochastic Petri network, that is when this will apply, but we will define those things later on, okay. So then I have that, this is where all the packets are getting stored, this is where all the packets are getting processed, this is my secondary buffer, that is all, right. This represents MM1B, as long as we will still call P2 and P3, right, with the condition that P2 plus P3 should be less than or equal to B, that is all I need, right, because this trigger will have, even if there is no input, it will keep on triggering, right, every 1 over lambda units or for mean units of time it will keep generating a packet, and the server will keep processing, and after processing we do not care what happens, we only care about the number of packets in the system for a given lambda and a given mu, that is what we want to look at, okay. So that is your how we can capture buffers in the system. The MM1B okay, right, what we saw before was only P2, but now the extra P3 is brought in to capture the limits on the particular system. And likewise we can also, when you are talking about communication protocols, network protocols, we can also emulate or model the passage of messages between 2 different programs, okay. So let us say there is program 1 or process 1 that is doing some sort of processing, right. So there is a conditional clause there, right, there is a dependency there, and then some sort of processing is taking place, and this is one program, okay. Then there is program 2 which is doing some processing, okay, it generates something and output of this transition goes there, and notice that I do not have to put always output on the right side, right, I can kind of do wherever I want to, as long as the arrows are clear we know what this is representing, okay. One more transition, one more place, and then finally this is done. So this is one message that is going from program 2 to program 1, and we could also have another message from here to here, no sorry, okay. This is a way of trying to show 2 programs sending messages to each other. So what will be the interpretation of this, can you think of? Let us say this is the sender, okay, and this technically need not be there, this particular loop actually may not be there. So what happens is, so when the sender, whenever there is a message to be sent, this transition triggers. So message is available, transition triggers. What does it do? It sends that message to other program. So basically there is a token being placed here, and let us say the token is always there, right, so it is not relevant. So as soon as you get a message, this is a sender, this is a receiver, right. Sender, this is the processing of the sending packet, all the transmission stuff, everything is happening here, message is now loaded there, and I can introduce delays on this arc itself, which we are not yet dealing with for now. So now there is a message available, this is some other internal condition which is true, so message gets processed by the receiver, and then the message gets received, and then some initial processing is done here, then some computation is also done here. After the end of the computation, what happens is, right, let us say that there is a token that finally gets placed, this could represent the ACK packet. So this represents the message being sent, right, this is where the packet generation is taking place, After sending the packet, what do I do with it? I buffer it, right? We all buffer it, right? Then I sit here waiting. So this transition will not trigger, will trigger only if there is a buffered packet and an acknowledgement comes from the receiver. I then go forward and I can remove this token from here, place the token here, right? This buffer can get empty. That will happen only when I get the return message in terms of an acknowledgement. This is like a simple stop and wait protocol. I send the message, wait for the sender to send the acknowledgement, I get the acknowledgement, I go forward, remove the token from here, put the token here. This could be simply post packet processing, right? Whatever that is involved here, this could be deleting the packet, recording delay and things like that. So this is the way that you can actually model the communication between two entities in a given system, right? So these are all the various things that you can do for a system. Is this communication model okay? Explanations are fine. So packet gets generated, gets sent, gets processed, some additional processing, acknowledgement gets generated, comes back, right? I could maybe remove this place, it is really not relevant, right? Just to show that some activities is going on. Basically I get it, process it, acknowledge it, send it back. I can really now release the packet from my buffer, from the sender's buffer, and then proceed further beyond that point. Okay. So like this there are lots of such combinations. Okay. So now what do we do with all this? So what is the point of all this diagram drawing, right? So we are interested in some mathematical properties of the system and then also finding out if we can derive some performance metric from the system. Okay. So what are the properties of a Petri net that one would be interested in? Okay. There are several, we will just list about 4 of them. Okay. The first is called the boundedness property. We would like to know for a given system, for a given marking, depending on the way all these transitions flow, right, would the number of tokens in a place be bounded? That is a question that we want to ask. That is a fundamental property. Why? Because if the number of tokens keeps growing unbounded, we know the system might end up unstable and therefore might end up being in having lots of delays and things like that. We see with the MM1, right? MM1 if lambda is greater than mu, it is going to be unstable, and therefore the queue size will grow very large, and therefore we will have unstable behavior. So that is something that is a property that we would like to investigate. And the second is so called safeness, which is a special case of this boundedness property. Okay, which says that system is supposed to be safe if will the number of tokens in any place exceed 1. That is also an important question. Will in any place the number of tokens by mistake exceed 1? Where you do not want that to happen is, let us say there is a manufacturing plant, right, some assembly is going on and you do not want to have say 2 parts, right, of let us say you are trying to build a car or maybe some other smaller component. You do not want to have 2 parts, 2 numbers of the same part showing up in a given assembly line on a given particular unit, right. One machine can only handle say one particular item. You do not want to have 2 items showing up on the disk at the same time. That can happen, right, because somehow the way the delays are done in the system, will it be the case that there will be one particular place with more than one token, which means more than one component to be built, which it cannot handle, which means the system might end, that machine may end up crashing and so on. Okay. So that is the so called safeness property of the system, which we may not relate yet in terms of computing, but there are probably other applications. And the second thing is whether it is deadlock free. In other words, will I enter a marking where from which I cannot get out of? We all know about deadlocks, right, where so I enter into a state or a marking where I cannot leave that marking and move to any other state of the system. So deadlock is also an important property of such a system. And the fourth is the so called reachability property. Okay. So given the initial marking m naught, m of t naught, that is initial marking, I want to know, can I reach this some other specified marking? Okay. Is it possible to reach some other marking, say MA. So what does that mean? It means this, right? Let us say there are 4 places in the system and the initial state is 0 1 0 0, okay. This is M of T naught for some particular system that we are modeling. I want to know whether it is it possible through a series of transitions, not just one transition, through a series of transitions can I end up in a state MA which will be say 2 3 4 4 or something like that, okay. This is for some reason I need to find out whether this can happen or not. This maybe should happen or should not happen, right, for whatever reason I want to know whether it is possible to go from this state to this particular state. So how do we do that? Is it possible, right? That is something that system should be able to answer with the help of this tool that we are talking about, right. So these are some of the properties of this Petri net that one would like to investigate, okay. So how do we do that? I will just stop after that. So the analysis methods, so given a Petri net and given these questions on these different properties, and how do we go about either stating the properties, that whether true or untrue, whatever it is, we have to show some proof. So the simplest way to do that is enumeration, right. I have a bunch of states, I have a bunch of transitions, so try all possible combinations, right. Start figuring the first one, then T1, then T1 T2, T1 T2 T3 and so on. So we can do just enumerate, and there are tools that will do that for you up to a certain extent, right. You can actually try enumerating to the extent possible. It becomes exponential, then of course you run out of time, but you really like to see whether this is enumerable in a reasonable amount of time to be able to answer this particular question. So that is one particular right way. And the second is sort of linear algebra techniques, where we use repeated matrix multiplications also can be used. I am not going into the details of those due to lack of time, but these are ways you can actually use linear algebra to find out, right, the probability of going from, or not probability, that what will be the next state. We saw this when we did our Markov chains, right, where given the initial state of the system, that vector, and then given the state transition matrix, right, if I apply it once, that is one set of transitions, I multiply by the same STM again, I get the next possible set of states, and this keeps on going until you find out the steady state probability, right. That is how we did that with them. Similarly, we can keep on trying to do this linear algebra technique of just multiplying by matrices over and over again to find out some sort of properties of the system itself. So that is something that we will again not cover about. And the third is actually simulation. So this is kind of interesting, right. We said we are going to use Petri nets to complement our simulation. Now I am saying that actually I will simulate the Petri net to find out these behaviors of the system. So in some cases, what the idea is that you can either, this is the same code, right, can be encoded as a Petri net with this more formal representation. If you look at your simulation code, is there a formal representation of states and transition between the states? You do not really have that, right. It is a bunch of functions and calling like that, but assuming you can represent that in a formal manner with these transitions and things like that, then you can actually bring in a simulator, right. We did this also as one of the first assignments. The tutorial, the assignment 1 was actually simulating the change of states, right. We started off with some state with some probability py, we moved to a different state, then to a different state and so on. That is simply Monte Carlo simulation, right. So likewise I can do that. I can start off with the initial transition, with the initial marking, and then when there are choices, right, I can keep on randomly choosing one of those choices and then try to simulate system behavior and then see whether it is possible to go to this particular state or some other state in the system. So that is also, these are all different techniques that one can use for analyzing the systems, right. And then the last technique is also converting this Petri net, or we will look at stochastic Petri nets. You can convert a stochastic Petri net to a Markov chain, a continuous time Markov chain, then you can use the continuous time Markov chain properties to actually solve problems or answer problems in the original stochastic Petri net, okay. So that is the first level introduction of what Petri nets are. So it is basically a collection of places, transitions and arcs that define system behavior. That is what we have seen now so far. We will come back, and the next lecture we will cover as to, we will look at an example that will show actually how we can model a system and how we can actually derive some performance metrics from those systems with the help of the Petri net model.